Cray since September, so it's 6 months I work at Cray. I'm based here at CSCS. So basically, I work in optimization and parallelization of the code, okay? So this presentation is divided in 2 parts, basically. The first part is an introduction to the Cray compiler, okay? So we will see, and then I did also a comparison with the other compilers, the Intel compiler, so how to use the flags and the different compilers. And then there is a second part, which is for the Cray performance analysis tools, what we call CrayPAT. So before starting, I want to, for my understanding, how many of you are familiar with the Cray compiler? Good. And Intel compiler? Good. GNU compiler then. Good, okay. Others? Just in case? All right, so, okay, let's Cray compiler. We will see, basically. So this is the overview of what we have inside the Cray compiler. So basically, we support most of the standard for the Fortran up to 2008, okay? So for the C++, we have up to 2003, so it's missing the new standard, the C++ 11, but still is working on. Then we support OpenP 3.0, is more or less everything from 3.1, okay, which is basically nested parallelism, few adds to the 3.0, and also part of OpenP4, which was, yes, it was mentioned for the accelerator stuff and the vectorization stuff, okay? So if you use OpenP for the automatic threading, you will see that there is a flag that you can specify so that the compiler can understand if you want to apply automatic threading, okay? And usually we support basically these things here, okay? So when you do automatic threading, okay? Now, we have full support of the Intel Standard Bridge, so the AVX vectorization and all the other stuff. The compiler is also able to support the NVIDIA accelerator, so it is not covered in this presentation. We support MPI 2.0 and the Pegasus languages. So here, basically what we have. We support OpenCC, hybrid programming, which means MPI and OpenP, in this case. Support for IEEE floating point arithmetics. Then, of course, on top of this, we have, as I said before, the Cray performance tools. So there is an interface to these tools, to the CrayPAT, the program library, and the version we will use is the Cray compiler environment 8.1, which was released in September last year, okay, which you can find also on the cluster. So what is to keep in mind very important is that there is an easy way using modules on the Cray cluster to switch between a compiler and another compiler, okay? So basically, these are the program environment. You can use module load, okay? You just connect to the cluster, and you can set which compiler, which environment you want, okay? In this case, Cray, GNU, or Intel, okay? On top of that, since you don't want to change your make file so that you will use, you know, G++ or ECPC or Cray, the compiler of Cray is Cray, capital C, okay? There are wrappers, scripts that you can use, and depending on which environment you have, this wrapper will load the correct compiler, okay? So you can use CC for the normal C compiler, capital C for the C++ and the Fortran compiler, and then you can specify which options, of course, depending on which compiler you're using, and then the files you want to compile, okay? So this is a clear example. For example, you want to compile Fortran, and then you can use FTN, okay? So always use this thing, always use this script, this wrapper, sorry, to the compiler and load the correct module, okay? There is, to check, but this is automatically load in your system, a specific module for the Sandy Bridge, and using this module will activate flags to have the correct, the best optimization for the Sandy Bridge in this case, okay, for example, okay? So automatically, when you load this module, we load also the environment, it will load also the flags, which are automatically specified for the compiler in this case, okay? Now, these are a list. We will go through all these with details later, but this is a list of the options you can have in the Cray compiler. So options for optimization, the usual all2, all3. Then there are options for the lining, okay? This is for the Fortran, and this is for C++. There are different ways to write these options. Here is the same. This is for creative listening, where you have optimization info. So you can have, you can dump in a file the information or the optimization which are done by the compiler. So you can see these options here. We will, as I said before, dash RM was already mentioned by Nathan. Okay, this is the way that we will see later how to use these flags. And then there are options for the parallelization, okay? So you can specify, for example, OpenP or not activate OpenP. These are owned by default, by the way, in the system. And also for automatic threading, okay? This is the way. More info, you can use the man pages, as usual. You can use the main pages on a given Cray compiler for Fortran C and C++. All right, so let's move on to the first part. Very important in lining. It was mentioned many times that it is very important to do vectorization. The good point of vectorization is that if you have an easy loop where you have easy arithmetic, so it's very easy to do vectorization. And once you start to have another, you call a function inside a loop, if the function is not inlined, then of course you cannot get any kind of vectorization. Clear, right? So what you need to make sure that all the functions inside a loop are possible to be inlined, okay? So the Cray compiler is very aggressive in this case. So there are flags that you can use, which is this flag here for the Fortran and this for the C++. And there are different levels. What is the case? The case that, of course, if you do aggressive line, so you line everything, okay? Of course, the executable will be very big, and you spend a lot of time to do this kind of operation, because you are copy your function many times where you are just calling this function. Okay, suppose we have a small function to do some kind of operation, okay? So you can decide which level of inlining you want to use. This is the full list, but you can use the main page to get this information. So what is important is that the default one is basically level 3, but then you can get even more aggressive using level 4. So you can see here the differences. And level 0 is basically non-inlining, okay? And level 5 is the biggest one. And then you can use also cloning of the function, where you can have different versions of the function. So you need to have this in place if you want to have then vectorization, right? Otherwise, the function will be non-inlined, and you will get a warning from the compiler, I'm not able to vectorize this loop because I'm calling a function, an external function, okay? So these are the flags to use. The other good point is that now, suppose you have a file where you have your loop, right? And you call a function which is in another file, okay? So when you compile your file, of course, the compiler doesn't know where is this function. It's not in that file. It must be in another file. So how can you do the inlining, okay? So if you remember from the Intel people, there is a flag in Intel compiler, which is called the interprocedural optimization, -IPO, okay? Of course, there is also a way to do this, and then they say that the inlining will be done at the level of linking, not the level of the compilation, okay? This is a way to do this with Intel, with the Cray compiler, which is basically using this option here, where you can specify which file, from which file you want to read the function. So if you are compiling the file A, and you know that inside the file A there is a function which is specified in the file B, okay, you can say, okay, do inlining and use the function from a given file or a given directory, okay? So you can shrink your case, your function to be inlined for a specific file, for specific modules, if you are using Fortran, okay? I'm C guy, by the way, so I use C, for example, but this is the same for the Fortran compiler, okay? The good point to keep in mind is that, of course, it's not possible to do cross-language, if it's not possible to do inlining between different languages, okay? But apart of that, you can use this option to specify the function to be inlined, okay, where they are and so on. Then, other important options are -3. This is the suggested option for the Cray compiler. And then the floating point level 3, we will see later on what that means, this option, okay? There are different options they can use. So let's say all 3 is a little bit better than all 2, okay? It can give you better performance. So yesterday we heard that it's best to use all 2, and then you can use all 3, but then you can have some problems when you do floating point operation, different results, and so on, okay? I would suggest to start with all 3 and use all 2 as debugging, for example. It can be that it's buggy the compiler, okay? Not necessarily to be an error in your code, okay? So I will start to be aggressive and then maybe go back instead to do the other way around, okay? If you optimize for all 2, then maybe you don't need to move to all 3, okay? Because you are doing the job that the compiler can do for you, okay? So if the launch is for free, I would go for free, no? All right, so the other option is to get optimization at the level of floating point, okay? So the suggestion is all for level 3, and we will see what does it mean. Then there are other more aggressive optimizations. So you can use more inlining and so on, but it's best not to use these aggressive optimizations, okay? So there is a floating point level 4. Here is, if you like, the explanation of floating point 3, which is basically optimizing for single precision, okay, if you know your code using single precision algorithm, okay? And then it's doing these optimizations, okay? So it can be the case that, of course, you are doing a association of the matrices operations. So if your formula is not with the parentheses, you can get different results. Just because the compiler is doing kind of optimization, for example, is using the reciprocal for the division and so on, so you can get different because of rounding, basically, okay? All right, so this explanation why the result can be different, okay? And as I say, there is a flag to change the level of optimization for the floating point, which is this flag here. You can get from all, so which means precise, basically, to 4, which is the best that you can have, but then the result, who knows what is the final result, okay? If you are, if you worry about this optimization, there is a specific flag in the compiler, so you need to set, okay, I will give for 0, 1, 2, 3, and see when the result is wrong, okay? Maybe you want to have one single flag to set in your application which kind of optimization you want to do for the floating point. This is the flag, okay? And there are 4 cases. So intolerant means that, okay, don't do any kind of optimization, okay? This is just for floating point, huh? Okay, you can specify minus all 3, and then you set this flag just to avoid floating point roundings, okay? Or maybe you want to compare 2 compilers, okay, results from 2 different compilers, okay? So if your application is really worried about this, so use intolerant. Otherwise, you can use tolerant, so you give the freedom to the compiler to do whatever he wants, okay? But, so the default is the best, as I said before. Otherwise, you can try the other optimization. And this is the default, so it's activating a lot of optimization, okay? So you can go down if you see there are problems. All right. Another good point, as I mentioned before, when I said for the aligning, is the fact that basically you can set which files to use to fetch the functions for the aligning. But there is also a way to produce what we call program library. Okay, so when you compile your code, you can specify this option here, -HPL, and then you specify here a directory where the compiler is putting all the informations during the compilation. So we call this program library, and we store all these informations, okay? Then he's using this information, for example, in other tools like Reveal, but then it can use also this information for the entire compilation, okay? So that it can use also, for example, for, as I said before, for the aligning and specific optimizations, okay? So in this way, you don't need to specify anymore the option for the aligning and so on. You just dump during the compilation. You need to specify one single library, and it will add all this information. So you have to compile 100 files. You specify for all these files in your Makefile, so one single line, this option, and it will dump during the compilation all these informations, which can be used then for the optimization of your program. So this is basically the explanation. So this is called whole program compilation. And then you specify this library. So it's dumping all the information you have during the compilation in one specific directory, okay? And so at this point, you don't need to use all this flag here for the aligning, okay? Because it's dumping all the information for all files, so it is able to understand where is the function, how to do the aligning, and so on. So this is a good option to use when you do compiling. But of course, then you need to produce this library. It can be very large. So depending where you are interested, you can string to only this case here, okay? Of course, the level aligning is still, you can still use this option, this flag here, where you specify the level of aligning, okay? Remember, from 0 to 5, okay? So this is kind of optimization then you will do when you use this specific flag. Okay, so for OpenMP, in our compiler is on by default. All the other compilers, they use a specific flag to have OpenMP. In the Cray environment, it's completely the opposite, okay? So OpenMP is on by default. If you don't want OpenMP and you have the pragmas, then you need to say to the compiler, okay, I don't want to use OpenMP, and there is a flag for that, okay? Which is this guy here or this guy here, okay? Or this guy here. So you can say to the compiler, okay, I don't want to use OpenMP in my program when I compile with the Cray compiler, okay? The pragmas there, then you will just ignore, okay? Auto-threading is not on by default, which means that the compiler can understand and can apply OpenP parallelization loops, automatic parallelization, okay? You can get this feature when you turn on these things, okay? Then, of course, as I say here, if you don't want OpenP, so make sure that OpenP is off and you can use these flags here, okay? Otherwise, if you are comparing Intel, which is not using OpenP on by default in the Cray, you will get performance on Cray just because of Cray. You don't need to specify any flag by default, okay? It's on by default, so keep in mind. There are a lot of directives that were mentioned already, but yes? Yeah, it will get for the maximum number of threads on the machine, which is 16 or 32 if CSMT is enabled. Okay, so.
Well, you control the number of threads at runtime and
Yes, X export and so on. If you have a set number of process, then it will get from from your program. Okay, that's for sure. Otherwise, it will read from the environment. Okay, but be aware of those facts. Okay, all right. So. Yes, so the option I mentioned before here is this number here, or this number here, is getting you performance when you do this compilation. So it can optimize also the OpenP part. So 0 means just ignore, okay? Then you can get 1, 2, 3, and so on to have better optimization of the OpenP part, okay? But doesn't mean this is not the number of threads, okay? Which is usually from the OpenP. All right, sorry. And these are some directives that you can use in your program to help the compiler to do optimization, okay? It's basically, any kind of compiler has the same optimization, okay? These are the cases for the Cray one. And then, of course, you can do man pages to see what are the options. So we can see other options. I find it pretty useful for use this guy here or this guy here. This is for their rolling, and this is for, but we also already seen blockable, and this is for the dependencies inside the loop, right? So that the compiler can vectorize if you put this specific directive or pragma. All right. Now let's see how to get feedback when you compile your code. Okay. The first way is to use, in case of loop. Okay. You can use this option here, -rm. Or you can use this option. This is for Fortran, this is for C++. So in this case, the compiler will generate given, if you are compiling a given source file, it will change the extension and you will get LST, okay? This was already described, okay? So this is the legend, okay? Then you compile your code. You can see, we will see in the practicals how to do that, okay? So don't worry. And you will see what's going on, which kind of optimization is doing. There are other flags there are in the practicals, okay? There are other flags that you can specify. You can understand which kind of optimization, how it's changing the code, okay? So that you can get a feeling what the compiler is doing, okay? Otherwise, you need to change the code, or you need to put pragmas, directives, to help the compiler to understand what's going on, okay? So, compiler is a kind of black box, but you need to understand what it's doing, okay? So, I will not describe what it's doing here, but it's quite easy, and it was already described. It's quite easy to understand from this legend what's going on, okay? So this is the piece of code, and then, of course, you have the output at the end, okay? Usually, you get here this asterisk here, this star here, which means that there is other information at the end, and you will see what's going on. For example, you can get useful information how to change the code, how to improve the code, okay? That's usual for any kind of compiler. Okay, there are several main pages, okay? Main pages specific for the scripts, for the wrappers, which are this guy here, okay? But then you will not get the information. So suppose you load the Cray environment, okay, or the Intel environment, or the GNU environment, and then you do main page, so these three guys will not get the information for the Cray if the Cray environment is there, okay? If you want to have main pages for the Cray compiler, you need to use these three guys here. Same for the Intel, same for the GCC, okay? Otherwise, you will get information for the wrappers, which tell you, okay, it's part of the Cray environment and so on. That's not maybe useful for what you want, okay? If you want to understand which version of the compiler you have, so you can use these wrappers. and then you can specify, let's say, -v if you are using the Intel and the Cray compiler, or minus version, so you can easily understand. It will tell you, okay, I'm using GCC 4.7, okay? You need to specify this option here, okay? So you can still use the wrappers, but then, of course, the option depends on which compiler, which programming environment is there. Okay, this is just to give you a comparison of the three compilers. So for listening means that you dump a file with all the information during the compilation for the optimization, okay? So you can use these two flags here. This is for Fortran, this is for C++ and C. Or you can get on the screen, so this was already mentioned yesterday for vector report, but there are others, okay? Optimization report, and you will dump in a file. So you don't need to read in your screen when you do make file. You will dump in a file, then you can do cut, for example. You can see what's going on. But there is also a way to do for GNU compiler. Then this is the usual way for Fortran. This is a suggested optimization. Okay, default for Cray. Otherwise, you can specify -3, which is here, and floating point 3. And for the Cray compiler, well, a corresponding for the Intel compiler is -3 AVX, okay? And the GNU compiler is more or less the same, okay? The GNU compiler is -m AVX, okay? Basically, it's using AVX, but Intel compiler is doing also specific optimization, okay? Which are not inside the GNU compiler. Here, aggressive optimization, well, I will not use -fast, but this is what they have, unless you need to specify a lot of options and try to avoid the options which are dangerous for you. For us, for the Cray compiler, it's very easy, okay? But for Intel, well, this is the comparison, but still, okay? There are other options that so that you can get the comparison. As I said, for OpenP, here is default. Here you can use -f OpenP, and here -f OpenP. Now Intel is using the same flags as GNU, okay? So previously they used -OpenP, now they add -f, okay? Just to avoid to have different versions for different compilers. There is also a way to use MKL. Yes, there was a description of what is the math kernel library, okay? So BLAS and all the other stuff coming from Intel. And of course, you can use the library, okay? The Intel compile the library from your Cray compile the code, okay? This is explained here. So you need to load a module to set this variable here for Intel. Then you load the program environment for Cray, okay? And then you can use this during your compilation, okay? And basically you will link to the MKL, okay? Pay attention that for FT it's a little bit different. So all these options are coming from this file, this web page here, where you just specify which system you have, which version, and so on. It will give you all the output, okay? It's an automatic way to generate all these options. As I said, for FT, it depends if you are using parallel or sequential version or the serial version of FT, and you need to use also the include, otherwise it will not find for you the correct version of the library. Okay, so the main point is that from your code compiled with the Cray, you can link to MKL, okay, if you want to use MKL. Otherwise, Cray has a different library, and you can link to our library, which may be better. This discussion will be tomorrow. All right. So automatically, the Cray compiler does static linking, okay? In principle, as you know, well, the difference is that when you produce static linking, of course, this better optimization, then your executable is fast, basically. And of course, who cares, because you assume that you are bound from the computation, okay? But of course, so this is the difference between the cases. But of course, you can set, and what is really important to keep in mind is that when you load the program environment, you need then to specify -L, where is the position of the libraries, and so on. It will be automatically done, okay? Then you use the wrapper, and this will be automatically done. Also, the -static flag will be automatically done, okay? So don't try to put a different flag, okay? Because all these flags for the compilation are automatically declared from module, the program environment. Unless you specify this option here, and then you will change, and you can do also shared libraries if you need, okay? That's the main difference. And yes, as I said, you can specify these variables here if you want to change the kind of linking. All right. So, again, once again, don't use directly the the compiler command, but use the wrappers, okay, and load the correct environment. That's the main point. So that everything will be set for the given cluster, okay? All right, questions? So it's easy because then in the practicals we will see that we have there's a makefile, and you can play and changing, for example, you just load another program environment, and you will use the same makefile, but of course, for example, you can do for Cray, and you will run for Cray, then you change the program environment, okay, module swap, and change the program environment, and this is an automatic way to do also this, okay, the practicals do everything for you. Anyway, you change the program environment, for example, you can combine then with Intel, and you will run again, and you will see, for example, the comparisons in performance and so on if you want. Okay, that's the point. Otherwise, of course, with the Cray compiler, then you can, or Intel compiler, you can set specific flags which are not common. So you would need to change the makefile, have different versions of the makefile. Okay, that's the point. Okay. All right. Question? Yes. Well, the reason is that, let's say, I'll just make you an example. There are some cases, okay, where it's better don't recompile everything and do linking of everything, right? So in principle, you can keep the same interface, and you will produce just a shared library. It depends which application you are targeting. In this case, as I say, these are high performance, so I would propose to use static linking. But if you're in a Linux environment, maybe you want to recompile your kernel, maybe you don't want to have everything static, unless you have 16 gigabytes of executable, which is not possible, by the way. Okay, so that's. And for example, if you use profiling and you want to instrument your code, most of the time, for example, you want to load different modules. So you know how to do that, right? You do export LD preload, and you will change, for example, the allocation. Okay, Cray has their own allocation, but if, for example, you can use a different allocation, allocator, sorry, like tcmalloc from Google, whatever, and this is a way to do that using shared objects, okay? But there is no real issue, at least at the moment, unless you really have huge applications. I don't think, I will be surprised if we have more than 300 megabytes of executable, okay? Anyway. So let's start with the second part. If you have other questions, then of course during the practicals you can ask them this, not a real problem. All right, so there was already a description yesterday of how it's important, how much it's important to understand where you are spending time, how to improve these, right? So Cray has different tools. We will see today very easy, and then tomorrow we'll go in detail how to use GUI tools and so on, okay? How to understand where you are spending time, how to get feedback for the compiler, understand this feedback, and then, of course, it's an incremental way to improve your code, okay? You cannot get in one shot all the information and then apply to your code. Basically, you do incremental improvement, okay? You want to understand how fast then you go in different parts. So all these tools help you to, so first of all, understand where you are spending time, so you can assist to develop the code. So these are the main points, help to understand the code. There are very easy tools, so there is a lot of man pages, a lot of information, a lot of documentation, so very easy to understand what the tool is telling you, okay? It's targeting scalability, so the idea behind is that if you have your MPI, we saw vTune. vTune is one single node, okay? But if you are in a cluster, you want to understand, for example, MPI problems, where you are running in different process, different MPI ranks, then these tools are targeting also scalability, so for the entire cluster, okay? vTune was just one single MPI. There was not MPI at all, basically. And the other good point of this CrayPAT is they are universal. So you need to use the Cray compiler. Of course, it's better if you use the Cray compiler. But by the way, you can use these tools also when you compile for GNU or Intel. They are not specific for a given compiler, okay? So these tools, they can give you information. It's a very easy to use, okay? All right, so this is the three main parts. So basically what you do, use this script. I will tell you then later how to use which kind of option and so on in your executable. So first, you load a module. Okay, we will see later. Then you produce your executable. Okay, then you use pat build, and it will instrument the code. And it will produce a new executable. Then you will run the new executable, and this will dump the informations in a file, right? And then you can use this pat report, which is another command provided by Cray, and you can see all the information in tables dumping on the screen. But there are also tools, as I said before, that you can visualize in very easy, intuitive, we would say, application. You can visualize all this information in tools. So one is the Cray Apprentice, and the other one is the Reveal, okay? Which are tools that where you can understand. There is also another command which is called pat help. It's going to give you all the information. It's interactive, okay? So you can run pat help and then see which information you want, just putting numbers and so on. And then, of course, this is the man CrayPAT, and you will get the man page for this information. So now let's go in detail how to use this, basically these two tools and these three steps, basically, okay? So yes, there was a description of what is tracing and what is sampling, okay? So I hope you understood the difference. The sampling is quite easy because you are taking your application, right? And every given amount of time, you dump the information what the application is doing, okay? So depends how long your application, you will get a given number of information, and then you will get the average. So it's a statistical point of view, okay? So you will get, okay, this function is spending a given amount of time, let's say 10% in average. Sampling is very fast, okay? Because you are not taking every piece of your function. It's just doing sampling, okay? And then you will get the average, okay? Understood? So if you are aware, for example, Valgrind, okay? You will run 10 times Drover because Valgrind is doing another things, which is tracing, okay? Tracing is getting you all the possible informations for all functions, okay? And then, of course, you will stay forever because it's very slow, because you need to dump a lot of information, okay? So how do you want to understand, for example, where you're spending time? So you do compilation, you do optimization, and so on, and then you do tracing. And tracing is so slow, then, of course, you will get different results just because it's dumping other information, no? Okay, that's clear. So there is, in Cray, an automatic way, which is called automatic profile analysis, which is able to understand which function, so where you are spending time. So for those functions, it's useful to do tracing, because maybe you want to get all the information. For the other function, maybe you want to do sampling. So you are not interested to do sampling for everything or tracing for everything, okay? You want to stay in the middle, basically. So there is a way with the Cray tools to do this automatic profile analysis, which is what we will do today, basically, okay? Tomorrow we'll go in details how to do or sampling or either sampling and tracing, okay? All right. Most of the time it's very slow. But then you will get all possible information because you will, for each call trace, with each function you will go call graph and so on. So you will see really what's going on. No, that doesn't need to be hardware-based. You can then add hardware-based. So tracing plus hardware-based, yes. So you can set how many, for example, floating point instructions and all the other stuff. This is part of tracing, okay, sure. And if you remember in VTune, there was an option to change the sampling, okay? By default, I guess it's 10 milliseconds. So if your application is running faster than 10 milliseconds, VTune will tell you nothing, okay? That's the point. Then you need to use tracing, okay? And when you use tracing, okay, then you can dump also the hardware counters, okay? It's very difficult stuff. Anyway, this is just a description. So here, lower red, this is what I think is most important things. Here, lower red, here, much more information, but of course, it's quite slow, okay? And then you need to understand all these informations, okay? But, I mean, this was already described. What is important for us is how we can deal with these two situations. And as I say, there is a way in Cray to do this very easily and understand which functions are important or not, okay? It's an interactive way, basically, okay? We will see how it works. So what do you do? Okay, use, as I said before, pat build. So you have a executable, okay? You load this module here, Okay, so you have your environment. So let's assume the Cray environment. So module load PRG environment Cray. You do module load perf tools. Be sure first to delete everything, okay? If you don't do make clean, whatever you have, then of course, if you use again, because this module will also set specific flags for the compiler to dump the information for the instrumentations. Okay? If you remember, the Intel compiler is the -G. GNU compiler is the -G as well. Okay? When you do module load perf tools, the -G will be added automatically. Okay? So you need to recompile your application. Okay? Make sure to do make clean. Otherwise, the make file will tell you, okay, but you are not changing anything. I cannot recompile. Well, I cannot recompile. It will not recompile. Okay? So will not require any change in the source code. Okay? You load the module, you recompile the application, and then you use pat build. Okay? There are groups of functions that you are maybe interested. For example, you want to understand where you are spending time in MPI functions, in math, and all the other stuff. We will see this later on. Okay? So basically, this is the idea. You have your executable, you do this, and we'll produce a new file with plus an extension plus pat. Okay? You run again this new executable, okay, and we'll dump a file with this extension here, where S here stands for sampling, okay? We will see in the protocols, okay? It's, believe me at the moment, but it's very easy. You don't need to change the code. Just load the module, recompile, and do pat build, the name of the application, the executable. And you will dump a new file, and then you will run the new file. Okay? This is sampling, okay? And you will produce this file here. Then, of course, you can use other options. And you can set, with this option, for example, if you are interested in a given part, given functions, and so on, okay? So you can shrink, and this is the tracing part. For example, in the tracing part, we are interested just in MPI or in heap memory usage. You can set these flags, okay? And with these flags, you can have information for a given part of your code. For example, -G, you can set MPI, and you will get information just for MPI. This is part of tracing. And the tracing case, so in the sampling case, was easy, right? And you will dump this file here. In the tracing case, you just specify which one you want, and you will dump a new file where instead of S, there is T now, okay? Tracing, okay? So these are the two different versions. And as I mentioned before, sampling is faster, tracing is slower, okay? But then, as I say, you don't need maybe to do tracing for everything. You just want tracing some specific function, you can use these flags, okay? With the APA, so the way to do automatic, there is an easy way. So first of all, you load the module as usual. Then you set, in the pat build stage at this time, you set -all APA and then executable. Okay? You will produce, again, a new executable. You will run this new executable. Okay? You will produce an XF file. Now there is not S, not T. If you remember here, there was a T for tracing, S for sampling. Now it's not producing anything because you are doing APA, okay? You will produce, then you use pat report on this file here. If you do pat report on this file, you will create two files. AP2, we will see, okay? And an APA text file. If you look at the APA text file, okay, then, sorry, we will see then what is inside this APA text file. Then what you can? Okay, in the first interaction, you are telling the system, okay, do instrumentations, okay? In principle, it's not sampling, it's not tracing. I want to understand which function I want to do with tracing, which function I want to do with sampling, okay? So in the first instrumentation, you will produce a new executable, and then you run this executable, and then you use pat report to produce this file here. In this file here, you will have flags to use for pat build to produce the the correct tracing, what is important for you, I would say, okay? So now use this file here to produce a new executable using pat build, okay? So you do -all the file APA, okay? No need to specify the executable anymore because the file APA is coming from this executable, and we'll dump for you a new executable plus APA. It's quite complex, but you will see in the practicals because there are several steps to do. What is important is that at the end of this phase, okay, there are 5 phases. So pat build, new executable with this option. With the new executable, then you run pat report. You will dump this file here, and you will use this file to do the new instrumentation here. Then you run, and you will produce a new file that you can read with the path report. Okay, so what is inside path APA? Okay. Sorry? It's automatically done in the first stage, because all these files are coming with all these files are coming with different sections, but the name of the file is the same, the executable. Thinking in this static linking. So of course, no need to read different libraries and so on. No. You need to compile module load perf tools, and then you just compile as usual. And then you use these steps to produce these files, and then you can analyze these files. We'll see how it works. Sorry, question. Sorry? Mm-hmm. Compiler linking? Sorry, what? Okay. Sure. Okay. But we will see in the protocol. So what is important for us is that in this way it's very easy, because as I said before, it's helping you instead to do tracing over everything or sampling. Maybe it's not useful to do sampling if you are interested in small function and so on. Maybe you need to do then tracing, because otherwise you get mess out. Okay, sampling every 5 milliseconds, 1 nanosecond, I don't know. Okay, so maybe you need to move to tracing, but then, okay, you will stay forever. So in this case, it's something in the middle. Then we will see the practicals is telling you all the steps to do, and then it's easy to understand. I mean, describing is not so easy, because, you know, you need to go all these steps. So when you run path report, you will dump a file on the screen where you have all these informations, basically. Okay, and then you will have these tables, for example, this table 1, and you will see in this table the time that we are spending for each function. This is dumped on the screen, okay? Of course, then you do rain direction, you dump in a file, okay? Then, as I said, tomorrow we will see there are graphics tools to analyze this output, okay? But this is just to understand that for today, okay? And you will see for different functions, for example, for different groups, what I mentioned before, which time you are spending, okay? So this is the output of path report, okay? Then the other thing, what is inside the APA file. We mentioned that there are flags. You can use these flags, right, during tracing to given functions, okay? This is a given module, okay? The APA file, with the APA automatic way, you will dump this file, and the system will understand, okay, this guy is spending a lot of time in this function, or not, right? So maybe he's more interested to do tracing for this function. Of course, if you know, then you can specify all this in your line. Otherwise, the APA will do for you, okay? And then, of course, you can change this to do the new instrumentation, okay? So the APA file is just a dump of options for path build. So you run path build. And the other interesting thing is that when you do tracing, you can specify again APA, and you can do it again, okay? It's incremental. So, as mentioned here, it's an effective flags that you specify to path build to do the tracing, okay? As I say, tracing only for these functions here, okay? These groups and these functions, okay? Not everything, okay? Otherwise, good luck. All right. So as I say, you can use path build, okay? And you will run again, and then on the new file, you can run path report to get a new output. And now is the new output from tracing, okay? So this is, for example, the new output that you can get. So the change in the table 1 now using the the executable from APA, okay, using the instrumentations with tracing, okay. All right. So this is a list of output files, basically. So we start with this guy here, which is basically when you're done when you do path build, okay. Then this is the output of path report, okay. This is also this output here. So it's for sampling, and this is for tracing, okay? Then you have this output here when you're running path report, okay? And APA, if you're running the APA, of course, output, okay? And this is the output, the executable, when you are running path build on top using the APA file, okay? And then, if I said before, if you run this, it will produce another XF file, and on top of path report, you will have the new output using instrumentation, tracing.
So all these files are output.
path report and path build. So path report, path build, depends if you're doing sampling or tracing. Path build, which is this is we will see tomorrow, is used by Reveal. Okay. If you are using APA, when you are doing APA, you will produce path report will produce this file here. And this guy here is done when you do the new instrumentation, so path build using the APA file. This is part of the practicals. I mean, there are all these steps are in a readme file. You will very easy to follow them.
This is the total list of the files. When you do the exercise, you understand which of them are created by the different steps. What's the reason to divide everything into so many files?
Okay, that's a reason for that. This guy here, and then of course the output on path report are text file. This guy here is coming from all the optimization you are doing. Okay, so it depends. If you're interested in given function, you can change this text file. So these are the executable, okay? These are the executable, okay? This guy here is a binary file. Okay. So in principle, you can reproduce this file here coming from here. So you can delete this guy here because you are using this. These are binaries, okay? Okay. So it's to save information, we say, okay? And this guy here is used from the other tools we will see tomorrow. It's a binary of the output on the screen, basically, okay? Path report will give you an output on the screen, so you can put in a text file. Otherwise, AP2 is the binary of this output, and then there are tools, GUI tools. We'll see tomorrow how to show these informations. Okay. This looks like strange, but you will see that it's quite easy because then we will see tomorrow there are a lot of options, so you can see what's really doing and which function is important for you and so on. Okay. And that's the main point. Okay. So again, questions? I mean, the good point is you can easily understand that VTune is getting you, because we have the comparison with VTune, but there are other tools on the market that you can use for doing this kind of things, right? So VTune is getting you all kind of information, and then you have the GUI. We will see tomorrow because we have the GUI. But in real life, maybe you really are interested to understand what's doing a single function, okay? So maybe you don't want to use GUI tools if you're running a cluster which is in US, then you need to have fancy things like BNC and so on, right? So we use command lines. And you don't need to change the executable. You just need to load the module, okay? This is quite easy in a Cray cluster, okay? You need to remember anything. You just need to run and then run the different tools, and you will dump the files, and you will understand what's going on. And tomorrow we will see how to do then, how to change tracing, right? So for expert, I would say, how to change sampling, how to visualize these informations.
So there's a lot of difference between technical implementation tools. This is a terminal version.
This terminal version, as I said, is for today. Tomorrow we will have the graphics. Okay. And you will see that our graphics is much better than VTune.
But you can do the same.
Sure. You will get the same information, but pay attention. Our tools can also have MPI. So you can be interested in MPI, you can be interested in memory consumption, you can be interested in a lot. We will see tomorrow there are a lot of options. And tools, we can show you these options. You can show call graph and can show you a lot of other information. Intel has another tool to do these things. It's coming from Vampire and Collector, they call. But yeah, that's. I mean, if you are familiar with the Vampire, you will understand what I'm talking about. These things are for entire clusters.